Welcome back. Today we will solve some algorithm challenges from the CSES Problem Set, and to be more specific, from the introductory problems section. So as you can see, we have here various exercises, and in each exercise we will get an assessment, we will get an input, and we have to provide the appropriate output. Now, on my GitHub page, I have published a repository with all the solutions alongside the documentation. So for example, this exercise, as you can see, I have here put together my approach, how I solve the problem, and the code. And you can also take a look at the code directly, like that. And it's pretty much complete, and I made it so it's very step-by-step approach, so it's understandable what I'm doing. And these two last exercises I haven't solved yet, so these will come soon. All right. And by the way, this video will be more advanced, so I won't go into basic syntax stuff from the Rust programming language. For example, I won't explain what a tuple is or what the map function does. But the more complex language constructs I will, of course, explain. So I suggest we speed up a little bit. So the first thing you need to do is you have to create an account. And I've already done that, so I will log in and introduction, and we have to set up the compiler for these exercises. As you can see, for Rust, we have to set some compiler flags. So let's do that. I will create a new cargo package. Let's cd into that. And now in the cargo toml file, as you can see, we have to set the edition to 2018. Like that. And as you can see, the optimization level should be 3. So we can set this by putting profile def opt level 3. All right. Here it says we need the rand package, but we don't really need that at the moment, so I will leave it like that. Let's build this. And as you can see, this is compiling. And over here we have an example program. So here are examples on how to solve the a plus b problem. So given two numbers a and b, calculate their sum a plus b. The first line of input consists of two space-separated numbers a and b. Note that the numbers might be negative, and the output should be a single integer a plus b. So if we input 3 and 5, we should get 8. If we input -6, 4, we should get -2. So I will copy this program, because again, this is just a test file. And by the way, inside of the source directory here, we can create a directory called bin. And this will store all the binaries, so we don't have to create a new cargo package for every single exercise. Right, so let's call this 00test.rs, and I will paste that in. Now, as you can see over here, they're using buffreader. To me, this is overkill for these exercises, so I will use another approach. But again, this is just for testing. So let's save this, quit, and now we can run this binary by typing cargo run / bin and the binary test 00test, and ensure that you omit the .rs file extension. All right. So as you can see, we now get input. We can put 3 and 5, and we will get 8. Let's try again. -6, -6, 4. We'll get -2. So this is working. All right. Now what we can do in source, we can remove the main.rs because we don't need that. And we are basically ready to go. And let me actually show you. So in the source directory, we have a bin directory, and over here we will store all of our binaries, basically the exercises. All right. So when we are done with an exercise, we can here submit. We can choose over here the binary or the RS file. We submit, and as you can see, this got accepted. All right, this was a test, and now we will start with the real exercise. Off at the first exercise. Let me put this over here, and let's see. Consider an algorithm that takes as input a positive integer n. If n is even, the algorithm divides it by 2, and if n is odd, the algorithm multiplies it by 3 and adds 1. The algorithm repeats this until n is 1. For example, the sequence for n equals 3 is as follows. So when we look at this sequence, we can see the first number is the input, right? 3. Then we check, is 3 even or odd? Now 3 is odd, meaning we multiply by 3 and we add 1, right? 3 times 3 is 9 plus 1 is 10. Now again, we check, is 10 even or odd? Now 10 is even, meaning we are dividing by 2, right? So we have 5. And again, 5 is odd, so we multiply by 3, 15, and we add 1, meaning 16. And this goes on and on and on until we reach 1. Until we reach 1, or until n is equal to 1. Okay? Now, your task is to simulate the execution of the algorithm for a given value of n. The only input line contains an integer n. Print the line that contains all values of n during the algorithm. As you can see, if we get the input 3, we will output this sequence, which is exactly the same one as this over here above, right? So I will create a new file in the bin directory. Let's call this 01 weird algorithm, like that. Now, the first task is to get user input, right? And the default way of doing that is creating an empty string and then we call the readLine method. As you can see, from standard IO in the standard input method, we call the readLine method, all right? And we pass a mutable reference to input. So that means that this has to be mutable, right? And we can unwrap this. And by the way, I won't do error handling here, so I will basically just unwrap because I assume that the input will always be proper, all right? So we have that. Now let's just print out the input. And let's execute the program, cargo bin. And by the way, instead of using cargo run bin like that all the time, I have over here created an alias. All right, so over here I have CR, and this will get expanded by the shell by cargo run. All right, just to save some typings. And by the way, a lot of people ask me what B is, and B is just another alias for the bad command. So with bad you can output a file in the terminal with syntax highlighting and line numbers. All right, so this will get expanded to bad01 like that. So let's execute. And as you can see, we get input. Let's put 10 and we just print out 10. So this would be the default way of doing that, but there is actually a more concise way of doing that. We can do that in a single line. So I will create a variable imp for input, and I will call the standard IO read to string method. All right. And then for the reader, we just pass standard IO standard in. And again, we will just unwrap. Alright, so we don't need that here anymore. And over here, I will just output this input. So this is actually, I will show you when I'm now executing the program and I put in my input. As you can see, it won't terminate. So we have to actually simulate over here an end of file symbol, and we do that on Unix-like systems with the Control D, right? And so as you can see, all the input over here will be outputted, because again, we have over here just print out all the input. And that's because this read to string method isn't actually for user input. It's more if we create, for example, a file over here, test file, and this is some input for standard in. Let's do it like that. So when we quit out over here and then we run the program, we can actually redirect the input from this test file, right? And then it will just print out all the lines, line by line, until it reaches the end of file symbol, right? So in every file, there is a hidden symbol meaning end of file. So the standard in knows that it reached the end of the file. So when we go with this approach, which by the way you shouldn't use, for example, in production, then we just basically have to simulate end of file by doing Control D. But this is working fine, so I will use this approach because this is more concise, right? So first of all, we got the user input, all right? Now, what we actually have to do is, because we are reading that to a string, so our input is a string, but we need over here to parse it to a number, because we have here to multiply and divide and so on. So we can't do that with a string. So let's trim first of all the input. So we remove the white space and then we parse it. And again, because parse returns a result, we have to unwrap. Now, because we are parsing over here, I need to define a data type, which I choose U64, right? So as we've seen, the first integer in the output is exactly the same as the integer in the input. What we can do is, first of all, we just print the input integer, right? Then we are repeating a process, so we will do a while loop. So while n is bigger than 1, right? Because when n is 1, then we have reached our goal. So while n is bigger than 1, and now we check, is n even or odd, right? So we check if n is even, and we do that by taking the input. Excuse me, this should be input. We do that by taking input and try and use this modulo operator, right? So if there is no remainder when we divide by 2, then we know it's even, right? So when it's even, we divide input by 2 and then we assign it back to input. And we can do that in a more concise syntax like this, right? And of course we have to make this input variable mutable like that. So when input is even, meaning the remainder of division by 2 is 0, then we divide input by 2 and reassign it to input. Otherwise, if it is odd, then we take the input, multiply it by 3 and add 1, right? And then reassign it back to input. Now in each iteration we want to print this out, right? So let me just do it like that. And by the way, we have to omit here the line, because the output should be on the same line, right? We don't want new lines over here. So let's see, we execute the program. Let's put in 3, and as you can see, this is the correct sequence. Now over here we have to put a new line to avoid this symbol. So let's write here print ln, like that. Now if we run it again, 3, as you can see, this is the solution. So let's submit that. And as you can see, this got accepted. Over here you can see the time it needed to execute the program. And because Rust is a very fast language in terms of execution time, as you can see, we don't even see how much it needed. And over here you can see the tests. So as you can see, over here we do it with 15, 27, 255, and we always got the correct sequence in every test case. Alright, see you in the next one. Missing number. You're given all numbers between 1, 2 until n except 1. Your task is to find the missing number. So the first input line contains an integer n. The second line contains n minus 1 numbers. Each number is distinct and between 1 and n inclusive. Print the missing number. So as you can see, the input, the first integer, will be the range, right? So we'll go from 1. So we will go from 1, 2, 3, 4, 5, where 5 is inclusive. Then the second line will be the actual integers in this range, except 1. So for example, we have here 1, 2, 3, 5. So the missing number in this sequence would be 4. And let me open my documentation. So if we have a range from 1 to n, and these integers are ordered and contiguous, right? So 1, 2, 3, 4, 5, and so on. The formula to get the sum of a range of increasing natural numbers is this formula, right? So n plus 1 would be, in our case, if we had 5 over here, n plus 1 would be 6. Times n, 5, would be 30, divided by 2 would be 15. So the sum of 1, 2, 3, 4, 5 would be 15. Now what we can do to solve this problem is we take the sum, right? And then the second thing is we take the sum of this, right? So we have the actual sum from 1, 2, 3, 4, and 5. So all of these together would equal to 15, right? And then we take the sum from the input. So in this case, this would be 11, right? 2 plus 3 plus 1 plus 5 would be 11. So when we subtract this, we will get the missing number. All right? So let's do that in code. Zero 2 missing number .rs. All right. So the first thing is we will take user input. So let's take the lines. And we will take 2 lines, right? So we will take 1, 2 lines as input. Then we take first and second, so we want this to be in a variable, the first line, and then the second line in the second variable. All right. So what we can do is we have here an iterator that got returned from the take method. And what we can do is just manually call next. right? So what we then have over here is we have in the variable f the first line and in the variable s the second line, right? So the first line is n, right? So we can parse this over here. And we parse that as U64. Now for the second line we want to take each of these substrings and parse it to an integer and then put it into an array. So we want to collect this into a vec of U64 integers, right? So if I print this out, now, let's say 5, 2, 3, 1, 5, right? As you can see, we have now a vector with the numbers over here parsed as integers. And we do that so we can actually, because we need here the sum of these inputted numbers, right? So let's delete that over here, and instead of collect we can do sum, right? So now we have the sum of these numbers. Let's put here U64. Like that. And then all we do is we apply this formula over here. So we have n times n plus 1, right? The first input over here. And divided by 2, of course. That's our formula. And then we subtract from it the sum of these numbers, right? So if I print out, let's run that, 5, 2, 3, 1, 5. As you can see, the missing number would be 4. Now we can make that more concise by putting this over here, over there. Like this, right? Let's go again, 2, 3, 1, 5. As you can see, the missing number from this sequence would be 4, right? So let's submit that. And this got accepted. And as you can see, we have passed all the tests over here. So these numbers can go really big, right? Here we are testing with 50,000 numbers, right? And the program found the missing number from this sequence in less than 0.01 seconds. All right, see you in the next one. Third one, repetitions. You are given a DNA sequence, a string consisting of characters A, C, G, and T. Your task is to find the longest repetition in the sequence. This is a maximum length substring containing only one type of character. The only input line contains a string of n characters. Print one integer, the length of the longest repetition. So as you can see, we get here a string. Now, what we want to do to solve this is we want to take this input and we put this into an array of characters, right? So we would have A, T, T, C, G, 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 and A. And this is in a vector, right? And then we can basically use indexing to check, is this equal to this? No. Okay. Then we have the longest sequence would be 1. Now in the next iteration we check, is t equal to t? Yes. So we have a sequence of 2. Now 2 is bigger than 1, so this will be our longest repetition. Now we check again, is t equal to c? No. So this stays like it is. C equal to g? No. G is equal to g, so we have 2 right there. And then again, g equals to g? Yes. So we have now 3 repetitions. So 3 is bigger than 2, so this would be the longest repetition. And now g is not equal to a, so we return 3. 3 is the biggest repetition in this DNA sequence. So in Rust, there is actually a method called peak method, and the peak method allows us to look into the future of the iteration. So we have over here the first element is 1. If we call peak, we see that we get back 1, so it saw the first element before iterating over it. And we can use that, or we can also solve this exercise by basically indexing. So what we are doing is we just check if S0 is equal to S0 plus 1, and then we check is S1 equal to S1 plus 1, and so on. We can use this approach, but I like the other approach more because it's more Rust-like, right? So let's call this repetitions. Like that. So first thing is we get some input. Like that. So this will be the input string. Then let's create DNA, and this will be our peakable iterator, right? So we are iterating over each character in this string, and we convert it into a peakable iterator, meaning we can use the peak method. And I will create 2 variables, one for count and one for max. As you've seen, we check the next character with the current character. If they are the same, we increment count by 1. And then we check, is the current count bigger than max? If it is, then max will be the current count, right? And because we are repeating this process until we reach the end of the string, we can use here a while loop, right? And because we are here returning an option type, we can use while let. Okay. Now, as you can see, in each iteration we are calling first the next, so we are iterating over a, okay, and then we call DNA peak, so we look into the next element and then we store it into current, C, and N next. And by the way, we have to use here reference because, as you can see, peak will return an option, reference, and then the item, right? So we have to dereference that, or we have to pattern match that with a reference. All right, so let's check if C equal N, then we increment count by 1, right? So if the current character is the same as the next character, we increment by 1, okay? So count in this case would still be 1 because A is not equal to T. Otherwise, if the current character is not equal to the next character, we compare next and count these two variables, right? We compare these and we will store the maximum of these two into max. The step I've showed before, right? So if count is bigger than max, then the count will be our maximum repetition. And then we have to reset count to 1, all right? And in the end, all we do is we print out max. This will then be our maximum repetition, all right? I hope this makes sense. Again, we are iterating over characters from this sequence of characters basically, right? And in each iteration we are iterating one time, and then we peek the next element, all right? We store these two into C and N, and then we check if C equals to N. So if the current character is equal to N, the next character, then we increment count by 1. So in this case, this is not the case. In the next iteration, when we call DNA next, this will be our current element, right? And when we call peak, this will be the next element. So C will hold T, this T, and N will hold this T. Then we compare, are these two equal? Yes. So we increment count by 1. We have now a repetition of 2. Now in the next iteration, C will be T, and N, this DNA peak method, will be C, right? So we again compare, they are not equal. So in count now we have 2, right? From before, we have incremented count by 1. We compare, max is still 1, but count is 2, right? So we then compare the maximum value and then store it or assign it back to max. So max will then be 2, right? Because count is bigger than max. Count is 2 and max is 1. So max will then be 2, and then we reset count to 1, right? So until this point over here, when we reach this iteration, the maximum count will be 2. So if the string ends over here, if the string would end over here, we would return 2, right? Because T and T would be the largest repetition, or the longest repetition in this case. And in the end, we just output max. Let's see if this is working. So let's run the program. ATT C GGGA. As you can see, the output is 3. So 3 is the longest repetition, and in this case this would be this sequence over here. Right, let's submit that. And this got accepted. Right, see you in the next one. Increasing array. You're given an array of n integers. You want to modify the array so that it is increasing, i.e. every element is at least as large as the previous element. On each move you may increase the value of any element by 1. What is the minimum number of moves required? The first input line contains an integer n, the size of the array. Then the second line contains n integers, x1, x2 until xn, the contents of the array. Print the minimum number of moves. As you can see, we get input 5, and this will be the amount of elements in the second input, right? And the second line contains n integers. So we have 3, 2, 5, 1, 7. So let's write that over here, 3, 2, 5, 1, 7. Now, you want to modify the array so that it is increasing. Every element is at least as large as the previous element. So we check over here. The best way is to start at index 1, right? This would be index 0. So we check, is this element smaller than this? It is, right? So we have to increase this element to be at least as large as this one. So we increase by 1. So we have here 3. So the vector now looks like that. Then we check 5. Is it smaller than the previous element? No. 1 in this case is smaller than the previous element, so we have to increase by 4, right? So then we have 3, 3, 5, 5, 7, and then the last one is 7 smaller than 5? No. Okay, and we are finished. Now we have here increased by 1 and here incremented by 4, so the total number of moves would be 5. Now what we can do is we just take a variable which counts the number of moves, right? So in this case we increment 2 by 1, so var will be 1. We have 1 move, and then we can set this element to the previous element, right? So 3, 3. And over here we have incremented by 4, so we increment this counter by 4, so the counter will be 5, right? Alright, let's see. This is number 4, increasing array. So first thing, we take input. Then we unwrap, we take lines, and we skip the first line, right? We don't need that actually, alright? And then I will do a flat map, and I will explain in a second why I'm doing that. So over here we are splitting white space, right? We are using here a flat map because we are splitting here on white space, right? So this will then be put in a vector. So we would have 3, 2, 5, 1 and 7, and we do that for every element. And we do flat map here because we want then to map over each number, and we want to parse this number to an U64. All right, of course we unwrap and then we collect, right? So we have now collected this second input into a vector of U64 elements. Then let's create the variable which is holding the counter, all right? And then, as I've said, we want to start at index 1, and we then compare the previous integer with the current one, right? And then we basically check, is the current element in the vector smaller than the previous one? If it is, then we assign to this variable the difference between the two integers. So for example, in the first iteration, the difference would be 1, right? 3 minus 2 is 1. So we assign that to this res variable. As you can see in the first iteration, we are subtracting the current element, in this case 2, from the previous element 3. So 3 minus 2 would be 1. This would be the difference. And we assign that to the res variable. And then what we have to do is we set the current element equal to the previous element, right? That's basically it. In the end, we just print out res, and then we will get the total number of moves we have taken in the iteration. All right, let's see. CR bin like that. All right, now let's pass 5 and 3 to 5, 1, 7. And as you can see, the number of moves would be 5. All right, let's submit that. accepted. See you in the next one. Permutations. A permutation of integers 1, 2 until n is called beautiful if there are no adjacent elements whose difference is 1. Given n, construct a beautiful permutation if such a permutation exists. The only input line contains an integer n. Print a beautiful permutation of integers 1, 2 until n. If there are several solutions, you may print any of them. If there are no solutions, print no solution. So, as you can see, we get as input n. This would be the number of elements we will output, right? In this case, 5. This will be the range. So we go from 1, 2, 3, 4, and 5. Now, as you can see over here, the difference is always 1, right? So this isn't considered beautiful. So it's actually pretty easy. We can, for example, do a for loop, and we start here from 2 and then incrementing each time by 2. So we have 2 and 4, right? 6 is not possible because 5 would be the last element, so we would be out of bounds. Now in the second for loop, we go from 1 and then increment again by 2 in each iteration. So 1, 3, and 5. And then if we concat these two ranges, we would have 2, 4, 1, 3, 5. As you can notice, the difference of each adjacent element is never 1, it's always bigger, right? So we have also to consider this if there is no solution, and it's basically when n is less than 4, right? So if n is equal to 2, we would have 1, 2, right? And no matter the combination, the difference will be always 1. So it's not possible to create here a beautiful permutation of this range. If we have 3, then it's the same thing, right? We have range 1, 2, 3. Now no matter how I combinate, 2, 3, 1, no matter how I combinate, as you can see, difference is 1 between these two elements. Difference is 1. Here the difference is 1, right? And over here same thing. So it's not possible. But if we have 4 elements, we can do a beautiful permutation, right? So in this case, for example, we start at 2, 4, and then 1 and 3. So we would have 2, 4, 1, 3. As you can see, the difference is never 1. All right. Let's create this file. This is number 5, permutations.rs. So again, let's take input. Read the string, standard IO, standard in, unwrap, and then we trim the input, we parse to new 64, and again unwrap. Alright, so we have an input of type U64. So if input is equal to 2 or equal to 3, then we print out no solution, right? Otherwise, now I've told you we can do a for loop, but I actually prefer to use a higher order function in Rust because it makes the code more concise. So we go from a range from 2 to n, right, to the input, and n should be included. So we put this equal sign here. And as I've said, we step by 2, right? We increment all the time by 2, right? And what we then do is for each integer, we just print out the integer, right? like that. And then in the end we print just an empty new line, so we don't have this symbol. Now if I run this, you can see that it isn't quite ready yet, but I want to show you just 5. Now we have 2, 4, right? 2 and 4. It doesn't matter if here we start with 4 and 2, it's the same thing. So we have 2, 4. Now we need the other integers, 1, 3 and 5. And in Rust you can chain iterators. So we did this iteration here, and then we print out these integers, right? So what we can do is we can chain a second iterator from 1 to included input, and again we step by 2, right? So what this does is we iterate, and let me actually, we iterate from 2 and we step by 2, right? So we have 2 and 4, and then we print these out, right? This gets printed out, and then let me 2 and 4, and then what chain does is when this finished, it will continue with this iteration. So we start at 1 and then step by 2, so we would have 3 and then we would have 5, right? And for each element in this iterator we print out the range. All right, so when I do this again, as you can see, we have a beautiful permutation. Let's submit this. And this got accepted. See you in the next one. Number spiral. A number spiral is an infinite grid whose upper left square has number 1. Here are the first 5 layers of the spiral. Your task is to find out the number in row Y and column X. The first input line contains an integer t, the number of tests. After this, there are t lines each containing integers y and x. So for each test, print the number in row Y and column X. As you can see, in the first input line we get the number of tests, in this case 3, right? And in each test we have 2 integers, one for the row and one for the column. So let's see, for example, 2, 3. So row 2, column 3 would be 8, right? 8. 1, 1 would be 1. And 4, 2, 4, 2 would be 15, right? So the first case, I want to check if the row is equal to the column, right? So if we get 1, 1, 2, 2, 3, 3, for example. So 1, 1, we will get back 1, right? 2, 2 will be 3, and 3, 3 will be 7. So the first guess is to put this into square, right? So we can take either row or column, it doesn't matter because both are the same, and we put this into square. In the first case, this is correct, right? We get 1. In the second case, 2 to the power of 2 would be 4, so we have to subtract 1. We will get 3, right? In the third case, 3 to the power of 2 would be 9, minus 2 would be 7. So how do we put this into a general formula? In the first case, we would subtract 0, right? And when we take a look at these numbers here, as you can see, we are subtracting each time either row or column minus 1, right? So 2 minus 1 is 1, 3 minus 1 is 2, right? So the formula here would be r to the power of 2 minus r minus 1. Or the same case could be made for c to the power of 2 minus c minus 1, right? So let me actually write this over here so we can keep track of that. R equal to c, right? So the formula here would be r to the power of 2 minus r minus 1, right? And now we can dissolve the brackets. So we can delete the brackets and we have to put this like that, right? And the same thing, c to the power of 2 minus c plus 1. So we have now the case for these diagonal numbers, right? Now let's check if, for example, the row is bigger than the column. For example, 2, 1, or 3, 2, or 5, 4, right? Or any other number, 5, 3 would also be like that. Now you have to notice here something. We are going in this direction, right? 1, 2, 3, 4, 5, 6, 7, and so on. If we would have more integers, it would continue the same path. Now, if the row, for example, row 2 is even, then, as you can see, we are from the diagonal, we are incrementing, right? So in the fourth row, we are incrementing. But if we have over here an odd row, then we are decrementing, right? So we have to keep that in mind. So the general case is if r is bigger than c. And let's check now if r is even, right? So if the row is even, 2 and 4 in this case. So let's see. Let's go with 4, 1, 4, 2, and 4, 3. All right. So 4, 1, 4, 2, 4, 3. First guess again, I would take this to the power of 2, this would be 16, right? So 4, 1, as you can see, we got the number. But if we take 4 to the power of 2 for 4, 2, row 4, column 2, we would have to decrement by 1, right, to get 15. And in this case, for 3, we would have to decrement by 2 to get 14. So maybe you notice something. We are here decrementing by column -1, right? In the first case, this is also true because 1 minus 1 would be 0. So 4 to the power of 2 minus 0 would be 16, which is right. So the general formula, if r is bigger than c, and if r is even, take r to the power of 2 minus c minus 1, right? C minus 1. And we can again dissolve the brackets like that. And that's our case if r is bigger than c and r is even. Let's check if r is odd, right? So for example, 5, 1, 5, 2, 5, 3, all right? So for 5, 1, we would get 17, all right? And If we again take 5 to the power of 2, we would get 25, right? So we have to subtract 8. Now, we could here try our first formula, alright? So if we take, for example, for 5, 1, we put 5 into this formula over here. So 5 to the power of 2 minus 5 plus 1. This would be 25 minus 5 plus 1 would be 21, right? Now we need 17, so we have to subtract from this 21, we have to subtract 4, right? Then we get 17. Let's see 5, 2, 18, so we have to subtract 3, 18. 5, 3 would be 19, right? Minus 2. And 5, 4 would be 20. So 21 minus 1 would be 20. So again, what are we subtracting here? How do we get to 4? It's simple, we subtract R minus C, right? The row minus the column. 5 minus 1 is 4. 5 minus 2 is 3. 5 minus 3 is 2. 5 minus 4 is 1. As you can see, we are subtracting from this number row minus column. Alright? So to put that into a formula, we take the first formula over here. Let me copy that. And then we are subtracting R minus C, right? Now we can actually dissolve the brackets over here. We have to make that plus. And now, as you can see, we have minus R minus R. So we have minus 2R. Like that. And maybe you notice here we have a binomial theorem, right? So we can write this like that. R minus 1. And we do that to the power of 2, right? And then plus C. This is exactly the same as this, right? It's just more concise. So we can delete that. And we have the general formula. If R is bigger than C and R is odd. Now let's see if C is bigger than R, right? If the column number is bigger than the row number. And first case, if C is even. So let's check for 1, 4, 2, 4, and 3, 4, right? 1, 4 would be 10, 2, 4 would be 11, and 3, 4 would be 12. So the column is bigger than the row and is even, right? So what we can do is we take this formula for the column and we put in 4, right? So 4 to the power of 2 minus 4 plus 1 would be 4 to the power of 2 would be 16, minus 4 would be 12, plus 1 would be 13, right? So we have 13 here. And then to get to 10, we have to subtract minus 3 in the first case, right? So we get 10. In the second case, we would subtract 2, so we get 11. Okay? And in the third case, we would subtract 1 and we get 12. And again, what are we here subtracting? We are subtracting this time the column minus the row, right? So 4 minus 1 would be 3. 4 minus 2 would be 2. 4 minus 3 would be 1. As you can see, these numbers. So it's actually the same formula as this, but with the column, right? So C minus 1 to the power of 2 plus R. And the last case, if C is odd, right? So if we have, for example, 1 3, 2 3, okay? Now 1 3 would be 9, 2 3 would be 8. So over here we take the column to the power of 2, which would be 9, and in the second case -1, right? 8. Or let's take 5, okay? It's better example. So 1 5 would be 25. If we take 5 squared, we get 25. 2 5 would be 24. If we take 5 squared minus 1, we get 24. 3 5, 23. So 5 to the power of 2 minus 2, right? 23. And so on. So again, in the first case, we subtract 0. So we subtract here row -1, right? 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. So in this case, we take c to the power of 2 minus r plus 1, right? Actually, we would write that in the formula minus r minus 1, right? But we can dissolve the brackets here and then change the operator like that. And these are basically all the cases. Now I want you to notice something here. If we have r is equal to c, then when we take, for example, this here, and because r is equal to c, we can write it like that, right? They are the same. So we have over here the same as this. And in this case, it's also the same, because we have seen c to the power of 2 minus 2c plus 1 plus r. And if we now have r equal to c, we can here write c, right? It's the same. And as you can see, minus 2c plus c would be minus c, right? So in this case, we have exactly the same formula. So we don't need here an extra conditional for this case, all right? And you will see what I mean when I write the code. So let's do that. I will go out 6 number spiral. All right, so let's first take input, and what we are doing here is we want to skip this, we don't need it, and we want then to put this in a tuple, right? In a tuple, and this should be U64 and this should be U64, right? And we store this in a vector. So this vector holds pairs, these pairs over here, right? And for each line. So in each line we get a tuple with 2 U64 integers. So again, standard IO, read to string, we unwrap lines, and then we skip the first one. I've told you we don't need the number of test cases, and then we do a flat map, and we split this string once at this. And we do here split once because this is very convenient. We get back a tuple of 2, because we get back a tuple of 2 elements, right? So, and we then map over these 2 elements in the tuple, R and C, row and column. And we parse, right? We have to parse both of them, and then we collect it into a vector. like that. So we have a vector of tuples, right? And each tuple is one line of input. So what we can do then, I will create here a result variable, which is then holding the result we can print out. And then for each line in the input, as I've said, we have a tuple of RC, row and column. And now what we basically do is just we check these cases, right? So let's start with the first one, if R is bigger than C, right? And then if R modulo 2 is equal to 0, meaning it's even, then res will be R to the power of 2, right? This formula over here, minus C plus 1. If it is odd, if row is odd, then res will be R minus 1 to the power of 2 plus C. R minus 1 to the power of 2 plus C. Okay? Now, if column is bigger than row, or if they are the same, because I've proven to you that it doesn't matter if both are the same, then we check if column is even, res should be this over here, right? So column minus 1 to the power of 2 plus R. Otherwise, if it's uneven, then res should be C to the power of 2 minus R plus 1. That's it. And then we can print out res. We do that in each iteration. And we should then have a working program. So let's see if this is actually working. CR number spiral 3 2 3 1 1 4 2. As you can see, this is the output we get. Let's submit that. And as you can see, this got accepted. See you in the next one. 2 knights. Your task is to count for k equals 1, 2 until n the number of ways 2 knights can be placed on a k by k chessboard so that they don't attack each other. The only input line contains an integer n. Print n integers, the results. So as you can see, we get here the integer n, right? So n is 8, so we go from 1, 2, 3 and so on until 8. So in each iteration we check for the possible combinations 2 knights can be placed, right? So for example, if we have a 1 by 1 chessboard, this would be a single square. It's not possible to place 2 knights on a single square, so the output will be 0, right? Now, if we have, for example, over here, a 2 by 2 chessboard, right? We can place 2 knights like that, right? 2 knights like that. We can place 2 knights like that, or like that, or let's take this like that, or last one like this, right? So we have 1, 2, 3, 4, 5, 6 possible combinations. Now in a 2 by 2 chessboard, the knights never actually attack each other. And if you don't know chess, let me explain to you. So we have here a knight, right? And the knight can attack in this way, in this way, in this way, and in this way, right? that, or in the opposite direction. So a knight can also attack like that, right? Like this, like that, and like that, right? So this is how a knight can attack. It's basically always either like this, 3 by 2, or 2 by 3, right? Like that. Now, first of all, we have to check how can we place the knights, right? We have here a 3 by 3 chessboard. How can we place 2 knights? So the first knight, actually, we can place at any location, right? So if we have a chessboard, K by K, okay? So as you can see, we have a K by K chessboard, where K is one of these integers in the range up until n, right? So in a 3 by 3 chessboard, we have K equals 3, right? Like that. So where can we place the first knight? In any location. So when we have here K and here K, then the first knight can be placed on K squared, right? On any location on the chessboard, on a K by K chessboard. Now the second knight we can place at any location. So if we place here the first knight, right? We can place the second knight at any location except this location over here, right? So the second knight can be placed at K squared minus 1. And this minus 1 is the place the first knight has been placed, right? So we would have the formula K squared times K squared minus 1, okay? Now we have to consider duplications. So if we place, for example, the first knight here and the second knight here, right? If we have another 3 by 3 chessboard, if we apply this formula over here, then if we place the second knight here and the first knight here, right, the opposite, then this would also be a possible combination, but we don't want to have duplication. So we already considered this exact combination, right? It doesn't matter which king is at which position. We don't care about the distinct knights. We only care about the possible combinations. So we want to avoid this kind of duplication. So what we do is we divide this by 2, so we avoid this kind of duplication, right? So let me write that over here. I will delete this. And let's see, we have here K to the power of 2 times K to the power of 2 minus 1, right? And we put that into square brackets, and we put that into brackets and divide by 2. So now we have all the possible combinations without duplication where 2 knights can be placed on a K by K chessboard, right? Now the second task is we have to subtract from this the positions in which 2 knights can't be placed, all right? And for example, in a 3 by 3 chessboard, right? 3 by 3 chessboard, if we have a knight over here, a knight can attack like this, or it can attack like this, right? So we can't place a knight over here and we can't place a knight over here. It's not possible, right? So to find out all the possible combinations where we can't place 2 knights, so we have seen that a knight can attack on a 2x3 block or in a 3x2 block, right? If we consider again a 3x3 chessboard, we have now to find out how many times a 2x3 block fits into this chessboard. Okay, so in this case a 2x3 block fits horizontally one time, right? And vertically it fits two times, right? 1, 2. And let's see 3x2. So 3x2 fits two times horizontally and one time vertically, right? So if we have again k by k, then we have over here k is 3 and k is 3, right? So 2x3 would be k minus 2 times k minus 1, right? And for the 3x2 block it would be k minus 1 times k minus 2, right? Because k is 3, so 3 minus 2 would be 1, and 3 minus 1 would be 2, and here the same, 3 minus 1 would be 2, and 3 minus 2 would be 1, right? So what we then can do is we can multiply k minus 2 times k minus 1 times k minus 1 times k minus 2, right? So this would then be 2k minus 1 times k minus 2. Or we could also change this, it doesn't matter, right? Now, inside a single 2x3 block or 3x2 block, a knight can actually be placed in two positions. Knight can attack like that, and it can also be placed here and it can attack here, right? So we have to consider two combinations, and we don't count the duplicates, right? So if we have the second knight here, we don't count that it can also attack this knight. We don't need duplications. So all we do is multiply this by 2, right? This over here by 2. Because again, in each 2x3 block or 3x2 block, the knight can be placed in two positions, in two attacking positions. Okay, so we would have 4k minus 1 times k minus 2. All right. So what we then do is just we take this and we subtract this formula. So 4k minus 1 times k minus 2, right? And this is all. We have found out all the possible combinations two knights can be placed on a chessboard without duplications, and then we have subtracted all the possible combinations without duplication on how two knights can't be placed on a k by k chessboard. So let's write the code. Seven two knights.rs. So again, let's first take the input. The input will be a single integer. We trim the input, we parse it, and we unwrap. Right, so we have now this input over here, right? Then, as you can see, we have to iterate over all possible. As you can see, we have to iterate over each integer up until n, right? So 1, we start at 1 and we include n, right, up until n, and then for each k, so in the first iteration k is 1, so we consider a 1 by 1 chessboard. On the second iteration k is 2, so we consider a 2 by 2 chessboard, right? We print out the formula, right? So we take k to the power of 2 times k to the power of 2 minus 1, and then we divide by 2 to avoid duplications, and then minus 4 times k minus 1 times k minus 2, right? And that's it. That's the formula. And now let's see if this is actually compiling and running. So cr bin 7, let's go with 8, and this panicked. Let's see why. Alright, we have to do here I64 because it could actually be negative in here, right? So if we do that again, as you can see, we get all the possible combinations. 2 knights can be placed on a k by k chessboard without attacking each other. Let's see if this gets accepted. That's it. We have solved another challenge. See you next time.